All right, we are going to move forward and talk about sequences and series. So it's kind of a completely different topic. So far in this course, we've been talking almost exclusively about integration. So in chapter, what chapter was it? Chapter 6, we did applications of integration. In chapter 7, we did integration techniques. Chapter 8 is about differential equations, and you do a lot of integration with differential equations. We skipped chapter 8. I'm going to come back to it later on in the course maybe. But chapter 9 is about sequences, sequences and series. And so it's kind of a completely different topic, but it's another, I would say like integration and sequences and series are the two kind of main topics of calculus 2. So we're going to spend some time in Chapter 9 talking about sequences and series. So an infinite sequence, or more simply just a sequence, is an unending succession of numbers called terms. So for example, this would be a sequence. 1, 2, 3, 4, 5, 6, 7, 8, right? Dot, dot, dot. Okay, on and on and on. Or 1, negative 1, 1, negative 1, 1, negative 1, 1, negative 1, right? That would be another sequence. In general, we write the terms of the sequence as A1, A2, A3, A4. You don't have to use the letter A. It could be B1, B2, B3, B4, whatever. Okay? And then the most common way to write a sequence is to find a formula that generates it. And this is called the general term of the sequence. So to give you an example of that, the sequence 2, 4, 6, 8 has general form or general term 2n. Since the nth term is obtained by doubling n, right? So this is the first term. The first term is 2. So you double 1, right? 1 times 2 is 2. This is the second term. So you double 2 and you get 4. You double 3 and you get 6. You double 4 and you get 8, right? You double 5 and you get 10. But you can tell what the 21st term, for example, is going to be 2 times 21, which is 42, right? And so we write it this way. We say 2, 4, 6, 8, dot, dot, dot. We'll actually write it like this. And instead of curly braces, we'll just put the general term, 2n, and then we'll use these subscript and superscript, n equals 1 to infinity. So let's practice finding the general term of some sequences. Okay, so let's do this for the sequence 1/2, 2/3, 3/4, 4/5, and so forth. Go ahead and give the video a pause and see if you can figure it out on your own. Okay, so here's my solution. So I noticed, this is the first term, and the numerator is a 1. This is the second term, and the numerator is a 2. This is the third term, and the numerator is a 3. So I think that the numerator is just going to be the same as the number, as the term number, right, which is n. The denominator, on the other hand, this is the first term, but the denominator is 2. This is the second term, but the denominator is 3. Third term, but the denominator is 4. Fourth term, the denominator is 5. So I think in each case, the denominator is the term number plus 1, right? So it's going to be n plus 1 for the denominator. So there's the general term, right? And this is how we would write down that sequence. Okay, here's another one. Let's do 1/2, 1/4, 1/8, 1/16, and so forth. So again, give the video a pause, see if you can figure that one out. Okay, here's my solution. So in each case, the numerator is 1. The denominator, on the other hand, goes 2, 4, 8, 16. So we're doubling the denominator each time. So notice that 2 is 2 to the first power, 4 is 2 to the second power, 8 is 2 to the third power, and 16 is 2 to the fourth power. So our first term is 2 to the 1. Our second term is 2 to the 2. our third term is 2 to the 3, and our fourth term is 2 to the 4. So our nth term is going to be 2 to the n, right? Okay. Let's do 1/2, -2/3, 3/4, -4/5, and so forth. Again, give the video a pause, but notice that this is the same thing as part A, but just you're alternating the signs. So you'll have to figure out how to do that. Give the video a pause, see if you can figure it out. So here's my solution. Okay, so first of all, as far as the numbers are concerned, I know that it's n over n plus 1 because I already figured that out. But how do I get the alternating signs? Well, the standard trick is to do this as a -1 to some exponent in n, right? So like here we want to get a positive value. That's going to happen whenever our exponent is even. But on the next term, we want a negative value. That's going to happen whenever our exponent is odd. So what we can do is, if I make this exponent n, then for the first term I'm going to have -1 to the first, which is going to be a negative. And that's not good because I want it to be positive. So if instead I make it n plus 1, then for the first term this is going to be -1 squared, which is positive, right? And then for the next term, for the second term, this is going to be -1 to the 2 plus 1, so that's -1 cubed, which is negative, okay? On the third term, it's going to be -1 to the fourth, which is positive. And on the fourth term, it's going to be -1 to the fifth, which is negative, right? And so this is good. This gives me the positive, negative pattern that I'm seeing. And then for the actual numbers themselves, right, it's just n over n plus 1. That's a little bit trippy, I think, the first time you see it. Maybe this isn't the first time you've seen it, though. But, you know, if you give it some thought, that should make sense. Of course, it goes without saying that if it's, instead of being positive, negative, if it's negative, positive, then you would do, you know, -1 to the n. Or you could have some more complicated patterns like positive, negative, or something like that. And then you have to do something fancier with that exponent. But this is the idea. Okay, and one more. 1, 3, 5, 7. See if you can figure that one out. Okay, here's my solution. So the first term is 1. So I might be tempted to think that the general term is just going to be n. But then the second term is 3, right? Not 2, so I can't just write down n. Then the next one is 5, and the next one is 7. Looks like I'm adding 2 each time. And one of the common tendencies is for students to try to give a recursive formula, which we'll talk about at the end of this lecture. And what I mean by that is that oftentimes they try to describe this term in terms of that term, right? So they'll say, oh, well, 5 is 3 plus 2, and 7 is 5 plus 2, and whatever. So they always get like the nth term is going to be the n minus first term plus 2. But that's not really helpful if you're trying to come up with a general formula, right? That's what's called a recursive formula. If we're trying to come up with a general term here, how else could we do it? Well, since we're increasing by 2, if you think about it like a graph, right? It's like this is like when you plug in 1, your output is 1. When your input's 2, your output's 3. So this is like the point 1, 1, 2, 3, 3, 5, 4, 7. And if you think about that, you're going to get a straight line, right? And the slope is going to be 2. The slope is going to be 2. So the slope is going to be 2. So that kind of tells me that I should call this 2 times n. But of course, that's not quite right, because if I plug in 1, I'm going to get 2. The 2n would give me 2, 4, 6, 8. But I want 1, 3, 5, 7. So it's always 1 less than that, right? So really, I should have 2n minus 1. That should be my general formula. And again, right, if you plug in 1, 2 times 1 is 2, minus 1 is 1. If you plug in 2, 2 times 2 is 4, minus 1 is 3, and so forth, right? So that's how general terms work. If you're thinking to yourself, well, but like, how do you do the problem? Like give me some step-by-step instructions on how to do it. There aren't really. You just kind of have to use your brain, right? You kind of have to like figure it out as you go. There aren't really like good step-by-step. I mean, for some of these things, there are kind of step-by-step things you could learn, but generally speaking, you just have to think it through in order to come up with these. Now, a couple things that I want to say about this. The letter N in, the sequence AN from n equals 1 to infinity, N is called the index. So N just kind of keeps track of what term you're on, so it's called the index. And you don't have to use the letter N. Any other symbol could be used, right? So AN from n equals 1 to infinity is the same thing as AK from k equals 1 to infinity, and that's the same thing as AI from I equals 1 to infinity. So these are all common letters that are used to represent indices, right? So N, K, I, J is often used for an index variable. So you can use any symbol. Another thing that I want to point out is that it's not essential to start the index at 1. So all of the work that we did here, we started the index at 1. But you could start from 0 or 5 or any other integer you like. And sometimes that can be quite useful. So, for example, instead of describing something like 1 over 2 to the n minus 1 from n equals 1 to infinity, you can just describe it as 1 over 2 to the n if you start your index at 0 instead of starting it at 1. And you can kind of pause the video and convince yourself that these two rules generate the same sequence of numbers, right? Like if you plug in 1 here, you're going to get 2 to the 1 minus 1, you're going to get 2 to the 0. So you're going to get 1 over 1, which is 1. Right? So the first number on the list, the first term in the sequence is going to be 1. Here, if you plug in 0, you're going to get the same thing, 1. If you plug in 2 over here, you're going to get 1/2. If you plug in 1 over here, you're going to get 1/2. So they're going to generate the same list, right? And again, you can convince yourself of that if you just write out like the first 5 or 6 terms of this, and then write out the first 5 or 6 terms of that. You'll see that they generate the same list, the same sequence. Which means that, there's always going to be more than one way to describe a sequence. So if you were doing these problems and you're pausing the video and you're coming up with something slightly different than what I wrote down here, you may not be wrong, okay? You may still have a correct solution. And if you're interested to know if your solution is correct, send me an email. Let me know what you got, and I'll let you know if it's correct. Anyway, so now, suppose that f of n is the general term of a sequence. So we usually use an to represent the general term, but really you can think of these like functions. They're just functions where the inputs are integers, okay? But anyway, so let's say fn is the general term of a sequence, and that f of x is defined on the entire interval of real numbers from 1 to positive infinity, okay? So the difference here is really subtle, but here I'm saying that the function is only going to be defined. Here I'm saying your inputs are going to be integers, right? Natural numbers in particular. And here I'm saying your inputs are going to be could be any real number, okay? But the rule f is the same, regardless of whether you're plugging in, an integer or a real number, okay? Well, anyway, if the limit as x approaches infinity of f of x equals L, then the limit as n approaches infinity of f of n equals L. In other words, you can kind of think of this f of n as like a subset of this f of x. And so you know that if the whole thing is going to some limit L, then the subset also has to go to some limit L, okay? Now, the converse is not necessarily true. It's not the case that just because a subset goes to some limit, that the whole thing goes to some limit. And let me give you a picture to show you what we're talking about here. Okay? So here's a picture where So I'm representing f of x by the continuous line, right? Because we're talking about all real numbers, and I'm showing f of n just by the dots, right? Just the dots on the line. So notice that f of x is going to this limit, and that means that the sequence also has to go to that limit L. Okay. On the other hand, here we have a scenario where you have a sequence that's going to some limit L, but the corresponding function f of x is not going to L. It's this weird kind of sawtooth oscillating thing, right? So it's not approaching any limit, okay? Anyway, the moral of the story, though, is this, right? We can use what we know about the limits of functions, of real valued functions, to determine if a sequence converges to some value in the long run. Okay, so basically, finding the limit of a sequence is the same thing as finding the limit of a function, pretty much. Okay, we use special words, but these words aren't new, right? But we say the sequence a(n) converges to L if the limit as n approaches infinity of a(n) equals L. And a sequence a sequence that does not converge to a finite limit is said to diverge. Okay, so it could diverge because either it's going off to infinity or negative infinity, or it could diverge if it's oscillating and not converting to any particular number. So I'm going to walk you through several examples. If this was kind of confusing, you'll see what I mean as we go through this next set of examples. Okay, so let's determine if the sequence converges or diverges. Okay. So, I'm sorry, I'm going to have to pause real quick. Okay. All right, so let's determine if the following sequences converge or diverge, and let's do this for n over 2n plus 1 from n equals 1 to positive infinity. So to determine if the sequence converges or diverges, all we have to do is take the limit, and if the limit exists and goes to a finite number, then the sequence converges, and it converges to that same limit. So let's see. Limit as n goes to positive infinity of n over 2n plus 1. Well, this is like a L'Hopital thing, right? Because this is an infinity over infinity. You could apply L'Hopital's rule, I suppose. Or you could just use the fact that it's a polynomial divided by a polynomial, so the limit is the ratio of the leading coefficients, right? So in this case, it's 1/2, right? So we would say this sequence converges to 1/2, right? So it converges, right? It converges. Okay, here's another one. Let's do sequence 8 minus 2n from n equals 1 to positive infinity. Well, limit as n goes to positive infinity of 8 minus 2n. Well, if you plug in bigger and bigger numbers, this is going to go to negative infinity, right? This equals negative infinity. So 8 minus 2n diverges. Okay? So hopefully that makes some sense, right? You're just going to be calculating limits. Here's another one. Let's determine if this sequence converges or diverges. So we'll do 1, 1/2, 1/4, 1/8, and so forth. So go ahead and give the video a pause and see if you can figure out if that one converges or diverges. Okay, So first of all, we have to come up with a general formula for this. I would write this as 1 over 2 to the n from n equals 0 to positive infinity. In fact, it's this sequence that we saw. It's this sequence that we saw earlier, and I'm going to write it. I'm going to choose to write it that way. I just think it's a little easier to think of it in that way. Okay. So then what we're going to do is take limit as n goes to positive infinity. And that goes to 0, right? So we would say 1, 1/2, 1/4, 1/8 converges to 0. Right? It converges to 0. Okay. All right. Let me give you 2 more, kind of hopefully more interesting ones. We'll see. So let's do n over e to the n from n equals 1 to positive infinity. Go ahead and give the video a pause, see if you can figure out if that one converges or diverges. Okay, so here we go. By the way, I mean it's interesting to like write down the first few terms of the sequence and kind of get a feel for it. This is 1 over e, and then 2 over e squared, and then 3 over e cubed, and so forth. I have a feeling that the denominator grows much faster than the numerator, so then I think that this is going to go to 0, but I'm curious like to know about how much those are. 1 over e. So 1 over e is like 0.368. 2 over e squared is about 0.271. And then 3 over e cubed is about 0.149. So yeah, I mean, these things are getting smaller and smaller and smaller. I guess that doesn't necessarily mean that they go to 0. To see if they actually go to 0, we can take the limit, right? We'll say, well, what's the limit as n goes to positive infinity of n over e to the n? This is definitely a L'Hopital thing, right? You can't even do kind of what we did in part A and just say, oh, ratio of the leading coefficients, right? You actually, I think you're kind of forced to use L'Hopital here. But okay, so by L'Hopital's rule, this is going to be 1 over e to the n. Oh, well, okay. And so then it's clear that this just goes to 0. So n over e to the n converges to 0. Okay, one more. I mean, as you can see, I think for the most part, this just boils down to, can you calculate limits? Although there are some slight differences that we'll see. Okay. So nth root of n from n equals 1 to infinity. Okay, so this is an example. This is actually a really good example of something that, if you were looking at the function f of x equals xth root of x, oh man, that thing is really badly behaved. It's like, because if you have if x is a negative number, oh man, like, yeah, that gets really bad. If x is a negative number, then in some places the output's not even real. But you're just going to be jumping all over the place, I think. It would be interesting to look at that in Desmos. I'm not even sure Desmos can do it. Maybe we'll do it in a second. But yeah, that's really interesting. So if you were looking at, like, for any real number x, this might be a problem. But but we're just looking at the whole numbers between 1 and, you know, infinity or whatever. We can make a list of some of these things. And this is kind of interesting too, thinking about the first root of 1. I mean, it's just going to be 1, right? And then you're going to get square root of 2. Which I know that that's like 1.414-ish, I think, but I'm interested in getting this in general. So so 2 to the 1/2 is, yeah, like 1.414. Then you'd have 3 to the 1/3. So you get cube root of 3, and of course 4th root of 4, and so forth. But this is going to be about, well, 1.414, 1.442. So it looks like it's kind of increasing. I wonder if that continues. So 4th root of 4 would be, no, it goes back down to 1.414. Actually, I think that's the same thing as the square root of 2. It is, right? Yeah, because 4 is 2 squared. So this is 4 to the, this is 2 to the 2/4, which is the same as 2 to the 1/2, right? But I wonder about the 5th root of 5. Now I'm really curious. 5th root of 5 is about, it's about 1.380. So it's starting to decrease again. I wonder what happens, right? It's like if you were looking at a graph of this thing and you really zoomed in on it a lot, you know, 1, 2, 3, 4, 5, but maybe this is 1 and this is 2. I guess I didn't really zoom in all that much, but you know, it's like you've got at 1, you're right here at 1. Then at 2, you would come up to like 1.4. At 3, you'd get a little bigger. At 4, you'd come back down. And then at 5, you come back down a little bit more. But I wonder, I kind of feel like the limit must be 1. Like I think maybe it's going to like come down and kind of do that. But anyway, let's check it out. Let's check it out. So we need to look at limit as n goes to positive infinity of the nth root of n. So we can think of that as limit as n goes to positive infinity of n to the 1 over n, if that helps. But 1 over n is going to go to 0, and n is, of course, going to go to infinity. So this is an infinity to the 0 type of situation, which is an indeterminate form. Here's how I like to take care of indeterminate forms like this, is that so I like to do this. So I say y equals limit as n approaches positive infinity of n to the 1 over n. And then to get this exponent down, I'm going to take the natural log of both sides. So I'm going to say ln of y equals limit as n approaches infinity of 1 over n times the ln of n, right? So I've just taken the natural log of both sides, right? Natural log of both sides. And of course, the natural log is really well behaved. You know, you can move it inside of the limit and all of that. And then I applied the power rule at the same time. So I brought this power down in front of the natural log. But hopefully it's okay with you. Anyway, now I get 0 times infinity, which is still indeterminate. But check it out, right? So we can fix that up pretty easily. We have ln y equals limit as n approaches positive infinity of ln of n over n. And now if we plug in infinity, well now we're going to get infinity over infinity. That's still indeterminate, but we can apply L'Hopital's rule to it. So I'm going to say, okay, so ln y, and say ln of y equals, this is by L'Hopital now, limit as n approaches positive infinity of Derivative of ln of n is 1 over n. Derivative of n is just 1. Okay, so that equals limit as n approaches positive infinity of 1 over n. And that equals 0. Now careful though, that's not our original limit. That's not the limit of n to the 1 over n. That's the limit of the natural log of that thing, right? So I'm saying ln of y is equal to 0. So since I know that ln of y equals 0, I know that if I exponentiate both sides, I'm going to get y equals 1. So the actual limit here is 1, right? It's 1, just like we thought. So limit as n approaches positive infinity of the nth root of n equals 1, and therefore the sequence nth root of n converges to 1. Okay, beautiful. So, so just reviewing a bunch of limit stuff. Now, here are some things that are cool about sequences that you can't necessarily do with functions, and this was actually a good example of that. My letters are all mixed up because I skipped a couple. I'm going to come back to those, but here's something cool you can do. So for one thing, a sequence converges to L if and only if the sequences of even numbered terms and odd numbered terms both converge to L. So, for example, the sequence 1/2, 1/3, 1/4, 1/9, 1/8, 1/27 converges. And that might seem weird at first because it seems like we're kind of jumping around everywhere. Like at first the terms are getting smaller, right? 1/2 and then 1/3 is smaller, 1/4 is smaller than that, 1/9 is even smaller, but then the term increases to 1/8 and then it decreases. But then it would increase again because the next term in the sequence would be 1/16, which would be bigger than 1/27. So from this point onward, it's going to kind of alternate, like smaller, bigger, smaller, or bigger, smaller, bigger, smaller. So showing that this thing converges is kind of tricky. And then the other thing is, how do you come up with an nth form for this, an nth term for this, right? That's hard. But if you notice what's going on, you've got, if you ignore every other term and you just look at the first, third, fifth, seventh terms, right? You have 1/2, 1/4, 1/8, 1/16. Okay, so the odd numbered terms are just 1 over 2 to the n, right? The even numbered terms are 1/3, 1/9, 1/27. That's 3 to the first, 3 squared, 3 cubed. So the even numbered terms are 1 over 3 to the n. Well, 1 over 2 to the n goes to 0, and 1 over 3 to the n goes to 0, and therefore this sequence is also going to go to 0, right? It converges to 0. So that would be the proof of that one, right? By a similar token, this series here is going to diverge. Why? Well, so we've got 1, 1/2, 1, 1/3, 1, 1/4. The 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, that part of the sequence converges to 0. But the 1, 1, 1, 1, that part of the sequence diverge, no, it doesn't diverge actually. That part of the sequence converges, but it converges to 1. So that's actually kind of interesting to say. So notice that. So this is for example 4. We've got 1, 1/2, 1, 1/3, 1, 1/4, etc. So notice that 1, 1, 1, 1, right? These are the odd numbered terms, right? That sequence converges to 1. And 1/2, 1/3, 1/4, 1/5, etc. That sequence converges to 0. So those are even. Those are the even terms. Okay? But because 0 and 1 are not the same number, the overall sequence diverges, right? You can kind of think of it like if you were to look at a graph of this one, it would look like this. So 1, 2, 3, 4, 5, 6, and this is 1. Right? 1, 2, 3, 4, 5, 6. Maybe we should go 7, 8, whatever. But the first term is 1. Second term is 1/2. Third term is 1. Fourth term is 1/3. Fifth term is 1. Sixth term is 1/4. Seventh term is 1. Eighth term is 1/5. Right? So you can see that it's diverging, right? It's diverging. You're not sure which. You're not sure if you're going down to 0 or if you're staying up at 1. It kind of oscillates between 1 and 0. So it diverges. So because 0 and 1 are not the same, the sequence diverges. Okay. So that's kind of an interesting thing. Another useful thing. So Squeeze theorem for sequences. This is something, we have a Squeeze theorem for functions as well. But we can also talk about a Squeeze theorem for sequences, and it works like this. So let's say that A, B, and C are sequences such that for all values of the index beyond some given value n, it is the case that an is less than or equal to bn is less than or equal to cn. So b is between a and c. In other words, what we're saying is that maybe for the first few terms of the sequence, this relationship doesn't hold. But once you get out past, say, like 100, right? Once you get to like the 100th term of the sequence or the 257th term of the sequence or something, once you get beyond that, this holds for all values beyond that, right? So if that's the case, right? So suppose that that's the case, okay? Then if A converges to L and C converges to L, then B also has to converge to L, right? It's the Squeeze theorem, right? So if these things are both going to L and B is between them, then B has to go to L, right? That's what Squeeze theorem is saying. So let me give you an example of that. So it says, use numerical evidence to make a conjecture about the limit of the sequence n factorial over n to the n, and then prove your conjecture. And Squeeze theorem is going to come into play there, and also this note that I wrote myself. But, okay, let's do it. I'm going to get a fresh sheet of paper. So the sequence we're looking at is n factorial over n to the n, from n equals 1 to positive infinity. Now, if you've never seen the factorial before, then let me just say n factorial, let me do this maybe in a different color, but so n factorial equals n times n minus 1 times n minus 2 all the way down to 1, right? That's what n factorial means. 0 factorial equals 1. We take that by definition. There are combinatorial reasons for that, right? It might seem a little bit strange. 1 factorial is also 1. But then 2 factorial would be 2 times 1, which is 2. 3 factorial would be 3 times 2 times 1, which is 6. 4 factorial would be 4 times 3 times 2 times 1, which is 24. Okay, so that's how the factorial works. So that's just kind of so that you understand how the factorial works, right? So this is how the factorial works. Okay. So let's see if we can figure out. Actually, we're supposed to come up with numerical evidence to make a conjecture about the limit of this sequence. So let's do that. So maybe I'll make a table of values or something. So I'll say sequence, or maybe I'll call it term number. And then and then the value, right? The value of that term number. So 1, 2, 3, 4, 5, 6, and we'll see if that's good enough to make a conjecture. But so let's see. So I'm going to do 1. You'll have to find the factorial button on your calculator, but I'm going to do 1 factorial divided by 1 to the 1. That's just 1, of course. That's not surprising. But now I can come back and I can replace these things a little more quickly. So, oh, that's interesting. It's 1/2. 3 over 3 cubed is 2/9. 4 over 4 to the 4th is 3/32. Ooh, okay. 5 over 5 to the 5th is, ooh, this is getting kind of nasty. In fact, I should go back and probably turn these into decimals, but I'm going to turn them into decimals. But it starts off, 1, 1/2, 2/9, 3/32, 24 625ths, 5 324ths. Okay, and it's going to continue on. But this is 1, 0.5, 2/9. So 2/9 is about 0.222. 3/32 is about 0.094. 24 625ths is 0.038-ish. 5 324ths is 0.015-ish. Okay, so things are definitely decreasing, and I think they're going to continue to decrease down to 0. So my conjecture. So my conjecture is that n factorial over n to the n goes to 0. All right, that's what I think is the case. Well, so here's the proof. So notice that n factorial over n to the n is going to be, well, n factorial we can write as n. Actually, let me write it backwards. Let me write it the other way. I'm going to write it as 1 times 2 times 3 and so forth, all the way up to n. N to the n, on the other hand, is just n times itself n times. So that's going to be n times n times n and so forth, all the way up to n. The number of terms up here matches the number of terms down there. Okay. I'm going to take out a 1 over n. And then that leaves me with 2 times 3 times 4 all the way up to n over n times n times n all the way up to n. Okay, and then notice that this is less than or equal to 1 over n. Okay, why? Well, because my numerator is clearly going to be smaller than my denominator. Okay, because all of the numbers that come before n are smaller than it, right? So when I'm multiplying 2 times 3 times 4 up to n, I'm going to get something smaller than when I do n times n times n all the way up to n. Whenever I have a numerator that's smaller than a denominator, that means the fraction is less than 1. And whenever I multiply something by a fraction less than 1, I get a smaller value, okay, than what I started with. So 1 over n times this fraction that's less than 1 is going to be less than or equal to 1 over n. Okay? So n factorial over n to the n is always going to be between 0 and 1 over n. Right? And so that means limit as n goes to infinity of 0 is less than or equal to limit as n goes to infinity of n factorial over n to the n, which is less than or equal to limit as n goes to infinity of 1 over n. Well, this limit is just 0. And this limit is just 0. So by the squeeze theorem, the sequence n factorial over n to the n goes to 0. And that's the end of my proof, right? Okay, so squeeze theorem, right? Squeeze theorem will work. Here's something else. This is true for sequences. It's not necessarily true for functions, right? But it's kind of a nice thing. So if the absolute value of some sequence goes to 0, then the original sequence itself also goes to 0. And so now I'm going to go back and do those two kind of alternating sequences that I skipped earlier. So let's take a look. So example 6, does the function converge or diverge? Well, let's see. Let's do this for the sequence -1 to the n plus 1 times 1 over n from n equals 1 to infinity. Okay. Well, I mean, first of all, right, if you were to write out some of the terms of this sequence, it would look like this. It would be, if you plug in 1, you're going to get a positive 1. If you plug in 2, you're going to get a negative 1/2. If you plug in 3, you're going to get a positive 1/3. Okay, so you can kind of see how this is going, right? So if you think about what the absolute value of that would be, right? So absolute value of -1 to the n plus 1 times 1 over n is just equal to 1 over n, right? It would just be 1, positive 1/2, 1/3, positive 1/4, right? It would just be 1 over n, okay? Well, this thing goes to 0, okay? So since absolute value goes to 0, the original sequence without absolute values also goes to 0. So it converges, right? It converges to 0. Okay? So this little alternating thing, it's not a big deal. You can, for all intents and purposes, you can just ignore it, and you can just look at this thing. If it goes to 0, then this thing converges, right? Now here you have to be careful because it has to go to 0 specifically. It's not enough for the absolute value of this thing to just converge. It has to converge to 0 specifically. So let me give you another example, okay? So let's say that we were looking at this situation. So -1 to the n plus 1 times n over 2n plus 1 from n equals 1 to positive infinity. Now we've already looked at this piece. We know that this piece goes to 1/2, right? So the absolute value of this thing does not go to 0, it goes to 1/2. So note that absolute value equals n over 2n plus 1, which goes to 1/2. Okay? So the previous theorem here, this so theorem 9.1.6 doesn't help. Does not apply. In fact, actually it kind of does in a way, because you can kind of think about this, right? So you know that the absolute value is going to 1/2, but this -1 to the n plus 1 is going to cause it to alternate. Okay, so thinking about the graph, you can kind of imagine this sort of a situation, where maybe you've got a positive 1/2 here and a negative 1/2 there, and the terms of your sequence, goodness, what would this look like? If you plug in 1, you get 1/3, right? If you plug in 2, you get 2/5, which is closer to 1/2. Okay, so yeah, so it's looking kind of like this, I think. You'd have kind of this situation going on, where individually, right, the pieces are getting closer and closer to 1/2 and negative 1/2, but then collectively, they're diverging because it's alternating, right? That's why in order for the original thing to converge to 0, the absolute value of this thing has to converge to 0, right? Or in order for this to converge at all, the absolute value of the thing has to converge to 0. Anyway, so this thing diverges. It diverges. Okay, so that's pretty much it. I did want to come back to the idea of a recursive formula. So as I mentioned, I think when we were looking at one of the very first examples, like when we were looking at this one here, you know, I said a common tendency is for students who want to describe this thing recursively. So they want to say, oh, this one is just 2 plus that one, and this one is 2 plus that one. So in general, you would say like an is 2 plus an minus 1. Well, that's a recursive formula. So a recursive formula for a sequence is one that describes the nth term by using the terms that precede it. And a very famous example of a sequence given by a recursive formula is the Fibonacci sequence, which you may have heard of before. But the Fibonacci sequence is given by this. So the first term is 1, the second term is 1, and then every term after that is going to be 2 terms before it plus 1 term before it. Right? So, so for example, we can write down the first several terms of the Fibonacci sequence, right? So the first few terms of the Fibonacci sequence are, well, the first term, like we said, is 1. The second term is 1. And then every term after that is going to be the sum of the term. How should I say? I mean, an is an minus 2 plus an minus 1. So it's the sum of the numbers 2 before it and 1 before it, right? So in other words, if I want the third term in the sequence, I'm going to add this plus this and get 2. If I want the fourth term, I'm going to add this plus this and get 3. If I want the fifth term, I'm going to add this plus this and get 5. And then I'm going to get 8. And then I'm going to get 13. And then I'm going to get 21. Okay. So that's the Fibonacci sequence, right? Okay. I think that's really all I wanted to show you about the, well, that's not quite true. So the second part says, show that an plus 1 over an is 1 plus an minus 1 over an. All right? So we want to show that a sub n plus 1 divided by a sub n equals 1 plus a sub n minus 1 over a sub n. Hopefully I wrote that down right. But let's see. Right? Well, I know that a sub n plus 1 over a sub n should be, well, a sub n plus 1 is going to be, it's the sum of the 2 terms that precede it, right? So it's going to be an plus an minus 1. And in fact, I'm going to write that backwards. I'm going to call it an minus 1 plus an. Okay? And then I think that's it, right? Because this is now an minus 1 over an. plus an over an. That's just 1, right? So that's 1 plus an minus 1 over an. Just switching the order of the addition. But that's that, right? Okay. So the reason that this is interesting is because this fact is used in the proof of what the limit of this sequence is. So it's not easy to figure out what the limit of this sequence is, but one of the steps in showing what the limit is to use this fact. And I'm not going to torch you any further, but it may interest you to know that this does in fact converge to this number right here, 1 plus square root of 5 over 2. This thing is called the golden ratio. And it appears in all kinds of things in nature. So you should just do a Google search for Fibonacci sequence, and all kinds of cool things will come up. But that's all I'm going to say about this for now. So yeah, we'll check in with you next time.